All right, welcome to section D. We're finishing up chapter 2 today, a little bit of a shorter lecture. We're going to continue talking about matter, and we're talking about changes in matter today, okay? We'll talk about physical changes and chemical changes. We'll start with physical changes. But in order to talk about physical changes, we need to understand what the physical properties of a substance is. Kind of the descriptive properties, color, texture, just things that are used to identify a substance, okay? Now, a physical change will change the appearance of that substance, but not the actual identity of the substance. It won't chemically change it. Any change in state is an example of a physical change. So for instance, if I have an ice cube, like the picture there. If I have an ice cube, it's still H2O. As that ice cube is melting in the liquid water, it's still H2O. Okay, so it's changed, the appearance has changed, the physical property has changed because the state has changed, but it's still chemically H2O, okay, so it's a physical change. Changing the shape or the size of something is also a physical change. I can tear this paper, I can crumple this paper, but it's still chemically paper. I've changed its appearance, but I have not changed its composition at all. Those are physical changes, okay? Chemical changes are a lot different. The chemical properties are what, are used to kind of identify it. It says a property that doesn't change no matter what sample you have of the substance. And some of those chemical characteristics that we'll talk about later on include boiling point, melting point, reactivity, and flammability. So if I have a sample of aluminum, it's always going to melt at the same temperature. If I have a sample of water, it's always going to boil at the same temperature, given certain other characteristics, okay? So those properties can be used to help identify a substance, okay? A chemical change actually changes the chemical composition of a substance. We also call chemical changes chemical reactions, okay? So if you pour vinegar into baking soda, you all know what that looks like. It foams up and it makes this frothy looking stuff. Well, what you're seeing is a chemical reaction. You're taking baking soda and vinegar that have their own composition, and they're actually reacting, and the bubbles are carbon dioxide. So what you wind up with is a substance that's totally different than what you started with, okay? Burning anything, I just like burning things, so it's a good excuse to start something on fire. There we go. This is changing the paper in such a way that's changing it chemically, okay? The ash that you see is carbon, and it's definitely changed the chemical composition of that paper. It's on the edge there, and what just fell off into my bowl of water is no longer paper. This part is, because I didn't burn it, but the part that I burned has been chemically changed, okay? Let's go back to the changes of state. Remember, all changes of state are considered physical changes. And this diagram here, you really should pause the video to be able to write all this down. This contains a ton of vocabulary right here. And it shows you the different changes in state we can have, okay? So let's go through this real quick, and then you guys can pause it and write it down, okay? So melting is a solid turning into a liquid. Freezing is a liquid turning into a solid. It's pretty self-explanatory, right? Pretty easy. I don't like this word right here, and I'll explain to you why. I like vaporization better. It's really hard to write on this. I apologize for the messiness. There we go. Vaporization. Vaporization is a liquid turning into a gas, and then condensation is a gas turning into a liquid. Boiling is a form of vaporization, but it only happens at specific temperatures, and it happens all throughout the liquid. When you put a pot of water on the stove and you boil it, you can see those bubbles. Those bubbles are forming all throughout. What's filling those bubbles is water vapor. So you're actually changing that liquid water into water vapor, and that's why those bubbles are, okay? So boiling is an example of vaporization, but so is evaporation. If you have a cup of water and set it out, the water on the surface is free to leave. The molecules of water on the surface of your pool or a cup of water or even in the ocean are free to escape from the rest of those liquid molecules and become gas. It's like, see you guys, I'm going to go hang out with my gas buddies. Still water, but it's vaporization is a better word to describe both of those things, okay? Then we have these two special ones on the outside. Sublimation is solid skipping the liquid phase and going straight to gas. If you have dry ice, it doesn't melt. It kind of emits this vapor, and that is solid carbon dioxide turning right back into gas carbon dioxide without the liquid phase in between. And then we have gas skipping liquid and going straight to solid. That's known as deposition. And that happens up in the clouds. Sometimes water vapor will turn directly into ice crystals without turning into ice first, or turning into liquid first, okay? One thing to keep in mind as we continue through this book, if you can see it, it's a liquid. Okay, specifically talking about water, if you can see it, it's a liquid. So even if you're boiling that pot of water, the steam above the water is not water vapor. That's still tiny little pieces of liquid water. They're spreading out, but then once you can't see it, then it's become a gas. Okay, so clouds are liquid water because you can see it. All right. Last thing, this law of conservation of mass. I think I referred to this a little bit earlier. Maybe that was another class. Doesn't matter. Basically, it says that mass cannot be created or destroyed. We're going to also learn about the law of conservation of energy that also states that energy cannot be created or destroyed. So basically what it's saying is that what you start with before a chemical reaction has to be accounted for at the end of the reaction. Even if some of it's burned away, the actual measured mass might not be the same. But then when you mix energy into account and, you know, the gas that's emitted and all that, it all has to be accounted for, okay? Which is really a simple explanation of Einstein's famous equation right there. The E is energy and the M is mass. And he's kind of combined these two laws, the law of conservation of mass that says, you know, the mass you start with is the mass you end up with. You can't destroy it. You can't create it from nothing. Plug in the word energy, the same thing. The energy you start with has to be the energy you end with. You can't create it from nothing. You can't lose it. Those two things are put together in this equation, okay? We'll talk a lot more about the energy one in a later chapter. And then we'll talk a little bit more about the mass one as well as when we get into chemistry and we start balancing equations. You have to account for everything that you started with in the end result, in the products as well, okay? And that is all. It's the end of chapter 2. Talk to you later.